So let me go back to what we were discussing last time. So it is circle compactification. The starting point was that we discussed closed strings. So the coordinate along the circle gets an addition here. Sorry. Yes. And the momentum is quantized, as we said. So the trick corresponds to and so essentially this split plus oscillators, which are already split in a left-right fashion. So written like this, we got alpha prime and so this way you define a left momentum and a right momentum. And the observation is that the partition function corresponding to a single dimension gets deformed into this sum and then there is a factor here which is square root of alpha prime over r. Last time we argued that the limit r going to infinity recovers the previous expression because the excitations depending on n become of infinite energy in that limit, so only n equals 0 is relevant. The summation over m can be approximated by an integral, and then you get this final form. So you see that basically here you get so if you write this expression in terms of tau, you get e to the pi alpha prime over 2 tau times this quantity, which I could call PL squared, and then tau bar, so alpha prime over 2 tau bar PR squared. And the first thing we notice is that the invariance under tau goes to tau plus 1 is granted automatically by this compactification because the factor that you will gain when tau goes to tau plus 1, you will get the factor e to the I pi times alpha prime over 2 and then PL squared minus PR squared. That's the deformation. And PL and PR are given by this expression. So PL or R is alpha is no, the way I wrote it is like this. It's M over R plus or minus n R over alpha prime. So if you take the if you take the double product of these guys, then you see that PL squared minus PR squared is essentially 4mn. And therefore, this quantity here, this quantity here, sorry, when I multiply by alpha prime, no, it's fine like that, yes. So this quantity here is invariant under tau goes to tau plus 1 if this expression here goes to 1. Now, people usually work with alpha prime equal to. Alpha prime equal to, this condition, it says that PL squared minus PR squared computed with this convention is twice an integer. That's why people talk about generalizations of this construction, because this kind of construction you can consider it also for multitori. So you would have an expression like q to the alpha prime over 4, or if you want with alpha prime equal to q to the 1/2 PL squared, q bar to the 1/2 PR squared, and then the invariance under tau goes to tau plus 1 tells you that the lattice should be even. It's a basic observation that Narain made in the 1980s, because people really thought that string theory was sort of unique originally, believe it or not. And then Narain noticed that there was a whole lattice, a sole choice of deformations which were associated to the parameters of this lattice compactification. Now here I'm referring to the type 2, because it's the one that is related to the orientifalls. In that case, these parameters that you have in general in a compactification of d dimensions are d squared. And you can split them into d times d minus 1 over 2 plus d times d plus 1 over 2. The second are the components of the internal metric, and the first come from the expectation values of the internal Neves-Schwarz form. These are constant deformations. The theory can be deformed in this fashion. In the heterotic string, you also have a 16 times d deformation, which correspond to internal Wilson lines. But lo and behold, you see that you have a very, very elegant formulation, because this is like saying that you have a Lorentzian lattice. So if you have a modular invariance and tau goes to tau plus 1, a Lorentzian lattice, which is even after this choice of alpha prime, you can define in this form. And the second thing is to see what happens if you demand the invariance under tau goes to minus 1 over tau. So let me summarize again. Invariance under tau goes to tau plus 1 can be stated in general, in this case in particular, but if you generalize the toroidal compactification to d dimensions, saying that you will get an expression like this, where the PL and PR will be squares of vectors. The invariance at tau goes to tau plus 1 effectively identifies an even lattice, but a Lorentzian lattice, because the condition for tau goes to tau plus 1 has, after you compactify d dimensions, d pluses and d minuses. Here you saw 1 plus and 1 minus in this case. So any compactification on an even Lorentzian lattice gives a partition function which is invariant at the tau goes to tau plus 1. The second condition is the invariance at the tau goes to minus 1 over tau, and this has to do with a basic result in mathematics, which can be decorated to various extents, which is the Poisson summation. I will remind you of this important fact, and I will try to sketch and argue that it gives you the second condition. Suppose you have a function f of x, and you consider the sum f of x plus n. And so imagine that this shape of this function is such that this summation is nicely convergent. For instance, some Gaussian peaks. Clearly, you build a periodic function, a periodic function of period 1, and you can expand it in Fourier series. So n in z, k in z, and then you have e to the I 2 pi I kx times ck. And the coefficient ck by orthonormality of this these exponentials in the interval 0, 1, you can write it as integral from 0 to 1 dx e to the minus 2 pi I kx sum on n f of x plus n. Now, you can also pull this term inside and write it as e to the minus 2 pi I k dot x plus n, because the second coefficient is identically 1, no? Because the product of integers is 2 pi. But this rewriting allows you effectively to extend the integration region from minus infinity to plus infinity. So in other words, this ck are essentially obtained by Fourier transforming f of x. And then if you put x equals 0 in this formula, you end up proving that the sum of f of n is the sum, I can call it of f dual of k, where f tilde of k are these Fourier transforms. Now, if you apply this thing to a sum like the previous one, then you see that this condition effectively reverses the radius. Reversing the radius means when you do this Gaussian integration, so it brings you from a lattice to a dual lattice. And now the second condition, in fact, is stated by saying that you have a consistent toroidal compactification if you compactify an uneven lattice, which is also self-dual. And these are underlying conditions. So you see that take these n-dimensional theories and go to lower dimensions, you find essentially solutions that depend continuously on a set of parameters. Far from being unique, the theory depends on this set of parameters which are moduli. And this pattern continues in various ways if the theory is supersymmetric. There's no back reaction on the vacuum, and you can go and compactify the theory to lower dimensions, getting theories depending on all these parameters. So for instance, for type 2b, the toroidal compactification of type 2b to lower dimensions would have the following partition function. So it would contain square root of tau 2 eta bar for the number of non-compact coordinates. Say originally they were 8 here, and then here there will be 8 minus n internal, say. Then there would be some factor which has to do the generalization of that factor there is the square root of alpha prime to the ni divided by the volume of the internal space. Would be this generalization of that sum, which is q to alpha prime over 4 pl squared, q bar to alpha prime over 4 pr squared. So you see, these are other ways of compactifying string theory to lower dimensions. Together with these ways, there is a brilliant idea that was invented in the mid-80s, which leads to the concept of an orbifold. So the simplest example of an orbifold is a tetrahedron. Tetrahedron, you can imagine, it's a sort of a deformed sphere. But the important thing about the tetrahedron is that the curvature is localized at these vertices. Now again, what one has under control is generalization of this internal surface that are compatible with the preservation of some supersymmetries. Okay. So the most very highly studied case is the case of T4 over Z2. These compactifications with supersymmetry, which means with a certain action on spinors that preserve some of the original supersymmetries, half of them in fact. This compactification is a singular limit on a compactification on a surface which is called K3. And then in 4 dimensions, there's a whole class of compactification that people have studied for years on Calabi-Yau spaces, which are obtained essentially taking not Einstein equations themselves, but the conditions for the supersymmetry transformations, and demanding that the bosonic configuration keeps the fermions fixed, because in the background the fermions are 0. If some supersymmetry transformation keeps the fermions fixed, it means that that's a symmetry of your background, if you want. And the advantage of that way of doing things is that they are first-order equations. Those first-order equations can be solved systematically, and they led to this idea of Calabi-Yau spaces, which are spaces which allow internally a covariantly constant spinor and lead to an internal space, say M, times Minkowski 4. So lead to 4-dimensional flat space with an internal space which has is Ricci flat. The reason I told some of you when we discussed privately is that you start from 10-dimensional string theory, which has no cosmological constant, and you want to end up in 4 dimensions. Somehow the internal curvature satisfies a sum rule, if you want. So if you compactify an internal space which is Ricci flat, you end up in 4 dimensions in a space which is flat. Again, everything is under control. In the presence of supersymmetry, there is no back reaction on your theory, and there is a long series of very sophisticated analysis of these systems, which revealed also an important symmetry of these spaces called mirror symmetry, which corresponds in 4 dimensions to interchanging the number of hypermultiplets and vector multiplets in n equal 2. By the way, I didn't tell you, but if you do Calabi-Yau compactification in type 2 theories, you end up in type 2b theory, then, or type 2a for that matter, you end up in 4 dimensions with n equal 2 supersymmetry. The first case that people studied was not this one, was doing it with a heterotic string, in which they ended up with n equal 1 supersymmetry for reasons that I highlighted before, namely the need to end up with n equal 1 supersymmetry, which allows chiral representations in 4 dimensions. Another crucial ingredient in this stuff, which was introduced by the, or suggested, if you want, by the Green-Schwarz cancellation mechanism, is that the tensor that you have in that theory, say in the heterotic case, which is of Navier-Schwarz origin, has a field strength which is modified, let me call it dB, is modified by Chern-Simons term. The Chern-Simons term is a combination of this type, which satisfies the following condition, that the omega is the trace of f wedge f. This is strange because you would imagine that dh should be 0 ordinarily. In this case, dh is not 0. And then, basically, Green and Schwarz noticed that here you should have another gravitational contribution to these two cancel the anomalies, where A is replaced by the spin connection. Now, if the signs are adjusted, essentially dh is related to the trace of f wedge f minus the trace of r wedge r. And if you have a closed internal manifold, the flux of the left-hand side should be 0, and therefore you have to arrange profiles for gravity and gauge fields in order that these things somehow cancel. And the first solutions were obtained with a very smart ansatz, identify the internal profile of A with a spin connection so that the cancellation is automatic. You agree with this, right? If I integrate, the left-hand side should be 0, and therefore you have a consistency condition here. So these things should add up to 0, and the easiest way to solve this condition is what people call under which A and omega are identified pointwise in internal space. And this led to a connection, say, between the heterotic string and models of grand unification with an E6 gauge group. What is very interesting is that the orbifold idea allowed to build exact string spectra corresponding to all to this smoother internal space. You can imagine that this smoother internal space is related to the orbifold by a singular limit, like I showed you for the pictorially for this tetrahedron. But there was a systematic construction starting from 10, then even from 11, because 11 was involving M theory, or at least what we know about M theory, the 11-dimensional picture that we have behind it. And so there was really a detailed study that took decades, to understand, as if you want, a translation between this geometrical data and the space-time data, which are essentially coupling constants, Yukawa couplings, and other details of the four-dimensional field theory. There is if you want, a dictionary between this geometry and this four-dimensional stuff. Yeah, but that's the six-dimensional case. Yeah, this is a six-dimensional case. But this is six-dimensional case is very important because there is a lot of novelties, including the fact, very surprising, that came out from open strings, that the theory can involve a generalized version of the Green-Schwarz mechanism with many tensors taking care. Maybe I will tell you something about the Green-Schwarz in a moment so that you realize what here. The four-dimensional case, for instance, can be related to a T6 over T3, for instance, or a T6 over Z2 cross Z2, for instance. Even that case can lead to four-dimensional, or a Z4, the other kind, there is a Z6, other cases like that. So the simplest case in four dimensions are T6 over Z3 or T6 over Z2 Z2. And those constructions lead to an equal one supersymmetry starting from the heterotic thing. There's a completely explicit thing. The problem is that all of these constructions are consistent with the picture that we gave before. Namely that there's no back reaction, nice, we have control, but they depend on parameters along the lines of what happens with this simpler case of toroidal compactification. The toroidal compactification, of course, does not reduce the number of supersymmetries. So when you start from 10 dimensions, if you start from the heterotic case, or type 1 for that matter, in that case, the number of supersymmetry becomes 4 in 4 dimensions. And so the resulting theory is not chiral. If you start from n equal 2, then you end up with n equal 8. In order to reduce the number of symmetries, basically, you introduce some judicious fluxes in the internal space. And this is what happens in these Calabi-Yau compactifications. Or if you want, you study the singular limits. But nonetheless, the end result is a flat space theory depending continuously on some parameters, which is nice because you control it, but not fully satisfactory because you have all these free parameters, which are called moduli, usually. The other thing that is not completely satisfactory is that to get models which resemble the standard model has been an extensive search, but they don't come naturally. They are there, models that are similar, but they're not the first thing that comes to your mind. There is something that is not direct. Now, one word about the Green-Schwarz mechanism to give you an idea of why the six-dimensional case is so important and widely studied. So the observation is the following, that if you have to study the idea is to start from 2D plus 2 and build invariant polynomials, say in 10 dimensions to be definite. These invariant polynomials contain trace of f to the 6, trace of r to the 6. F means the two form f mu dx mu dx nu, and the same thing for the gravitational part. Or they can also contain reducible terms, like for instance trace of f squared, trace of f to the fourth, and similarly mixing trace of r squared, trace of r to the fourth, trace of r squared cube, and similarly here. Given any type of these terms, you can get the anomalous contribution by a descent method, if you want. So the idea is the following, that for instance, trace of f squared, this quantity is the exterior differential of this omega that I wrote here. I call it now omega 3. It's a 3 form, no? Trace of S squared is a 4 form. It's the d of omega 3. Now, this quantity is gauge invariant, and omega 3 is not, but delta omega 3 is omega 2 lambda, if you want, alpha, say. And in this case, is the trace of lambda dA, alpha dA, sorry. So if you go down a term like this, if you push it down to 10 dimensions, what do you do first? You say you take a trace of S squared, you write it as d omega 3. You already go down 1 dimension. This d can be pulled out because d of f to the 4th is 0. So starting from d equal 12, say, I give you this example, no? In which you start from trace of f squared, trace of f to the 4th. In 11, you get omega 3, trace of f to the 4th. Why? Because here I would get exactly d of omega 3, trace of f to the 4th, but the d can be pulled out because f to the 4th is, the trace of f to the 4th is closed. So this way you go to d equal 11. And then if you go down here, this quantity becomes trace of alpha dA, which is a 2 form, times trace of f to the 4th. And this is one of the contributions to the 10-dimensional gauge anomaly. This contribution can be cancelled by a local counter term. The reason is the following. Comes from this modification of the field strength. Because if the modification of the field strength contains this term, say, forget about the gravitational one for the moment, which is a higher derivative. So if you're working with dB minus omega 3, then the question is what happens to B when you perform a gauge transformation involving the gauge parameter of the gauge fields, no? The variation of this quantity, we said, under gauge transformation of the gauge fields is of this type. So H cannot be gauge invariant unless delta B transforms proportional to the trace of alpha dA. So when you add this Chern-Simons modification, the gauge invariance of H requires that B gets, so to speak, merged with respect to the transformations of the gauge fields. And then you see that this term here can be regarded as the gauge variation of B wedged this way. And so it can be cancelled if you take the theory and add the local term of this type. And that's the key idea of the Green-Schwarz mechanism. The cancellation that is automatic at the level of the string amplitudes in the large effective field theory can be understood as the result of the presence of local counter terms that can take care of part of the anomaly. In lower dimensions, so in 10 dimensions, in the type 1 superstring, you have only one mechanism of this type, one, say, effect of this type. But already in the U32 theory, you have 3 contributions of this type that cancel part of the anomalies. In particular, that theory contains an anomalous piece that, if you want, eliminates the U1 from the gauge field, from the gauge group. So the gauge group is not U32 effectively. It's SU32 because the U1 disappears due to a mechanism like this. And in lower dimensions, in 6 dimensions, the theories can contain a number of self-dual or anti-self-dual 2 forms that need to cooperate to cancel the gauge anomaly. So that's why it's very rich. It has been studied because it's more constrained than the 4-dimensional case. But lo and behold, you continue to deal with the same type of problem, namely that the theory doesn't back react, is well defined, but supersymmetry that helps a lot in many respects leaves all these undetermined parameters. So if you want, the issue is what can we do if we break supersymmetry? So let me do first of all one case. It is more conventional, but we look at it from the string theory vantage point. What I told you about the one-dimensional torus is the basis of this construction. So we imagine to take type 2b, to go from 10 to 9 dimensions, and we try to implement the Scherk-Schwarz mechanism, which, if you want, in the simplest of possible terms, is the following. Take a circle and consider a periodic moding for bosons and an anti-periodic moding for fermions. Clearly, this will separate them in mass. And you may say that if we are good, we can separate them a lot in mass. So let's try to do that. So the basic starting point, no, I don't want to erase that. The basic starting point is what I showed you there. So this is, let's try to, already in the simplest case, to break supersymmetry. So we start to consider this partition function. Now I will write it in a slightly different notation. And maybe I can start like this. No, let me write it in slightly different notation. It's more convenient. For lambda mn means what I had there. And here I added eta bar. So this part here is modular invariant. There is a different way of presenting it when modular invariance is manifest. But under tau goes to tau plus 1, I showed you that this is the case, sort of. And under tau goes to minus 1 over tau, it has to do with Poisson summation, but you can see it. The rest here will concern the other dimension. So instead of having square root of tau, eta bar to the 8, I will have it to the 7th. So this is the partition function that I'm considering. Okay? Now I perform an operation which is also teaching you about what orbifolds are like, but in fact this is called a shift orb. And what is this operation? It only has factors. I will not write the other factor. So I consider V8 minus S8, absolute value squared. And I do 1/2 plus the deformation of this. What do I do? To plus 1/2 V8 plus S8. So if you want, and then this term here, I write it as minus 1 to the m lambda mn. Minus 1 to the m lambda mn means it's a shorthand for saying that the condition gets a minus 1 to the m q bar to alpha prime over 4 times the other one divided by theta bar. So in other words, I deform the internal contributions, flipping sign alternatively to terms which have momentum quantum number even or odd. Okay? I could do the same thing for the windings. Let me do it with the momenta. Okay? Let me see what happened. Let's see what we achieve. So let's expand the bosons in this case. And then you will get 1 plus minus 1 to the m over 2 lambda mn. And the fermions So the schematic description tells you quantum numbers, and this is odd. Doesn't seem what I told you before. Before I said that one of them have momenta, the other one shift 1/2. But it's just a redefinition of what R means. Rescaling R, we can go from one to the other, no? Because in this case, this sum here means the sum of M and N, Q to the alpha prime over 4. Instead of having M, what it was, it becomes an even number. Q bar similarly. And the second sum is the sum on M and N divided by eta bar like before. And so you have Q to the alpha prime over 4, 2M plus 1 R over alpha prime squared. And so you see that up to a reinterpretation of the radius, saying that the radius, say, is twice another R prime, this, in terms of this R prime, or this R over 2 if you prefer, has all the integer quantum numbers, and this has integer plus 1/2. In any case, I've separated them in mass, right? Okay? With respect to the original toroidal compactification, when I do this operation, you see that the Bose and Fermi excitations are separated in mass, which is the first thing you want to do when you do toroidal compactification, when you do supersymmetry breaking, right? You want to separate them in mass. However, the problem is that it's a theory of closed strings, and so you cannot stop here because it's not modular invariant. You have to add the twisted sector, as it said. So let's add the twisted sector and see what happens. Here you have to believe me a little bit because I will have to do a computation which will require a Poisson summation. But I mean, it's something that can be reproduced simply. We do it starting from this expression here, because these are simple to... So the first term is modular invariant by itself, and so we leave it as it is. Let's look at the second guy. So when you do this operation, you lose modular invariance. And so you have to... maybe I will write it explicitly. Sum on M and N, Q the alpha prime over 4, M over R plus NR over alpha prime, Q bar to the alpha prime over 4, M over R minus NR over alpha prime, divided by eta bar. Now, if I do an S transformation, so I let tau goes to minus 1 over tau, this term, we know it from what we said before, becomes O8 minus C8. And now I tell you that what happens in this sum, that by Poisson summation, what happens is that you get the following expression. Sum, the n is shifted by 1/2. And then if you do a tau goes to tau plus 1 transformation, this guy becomes O8 plus C8 because these guys are different by 1/2 in mass. And then you get a similar sum here with this shifted n, but multiplied by minus 1 to the n. Sorry, minus 1 to the... I'm not sure. I may be getting confused. Let me check one moment. I think it's minus 1 to the n, but I'm not sure. I'm not sure. just give me one moment to fix this coefficient. Come on. Let's see. No, it's minus 1 to the m, fine. Minus 1 to the m times the same expression. Okay? So let's see what happens if I look at the bosons and the fermions. Okay, so the bosons will get O8 absolute value squared plus C8 absolute value squared. And now, in this symbolic notation, you get 1 plus minus 1 to the m over 2 lambda m n plus 1/2. And then you get minus 1 to the m over 2 lambda m n plus 1/2. And this is very interesting because do you see what happened, what price you pay for doing this? That in the twisted sector, there is a tachyonic sector that appears. Doesn't mean that you have tachyons, but you have a tachyonic sector. And then what happens? In order to separate a lot in mass, this sector, you better make R as small as possible. You can see it from here. Because in this sector, M even or M odd have very different mass. No? They have a mass difference of order 1 over R. So you try to make R as small as possible, you separate a lot in mass these states, but then what happens? That in this case here, the tachyon gets a mass which is, gets a contribution from the lattice, which corresponds to the leading one, M equals 0, N equals 0. So the mass gets a contribution which is R over 2 alpha prime, if you want, from that term. So in other words, if you reduce R, you cannot lift the tachyon to the massless level. So you get an instability. So if you do this compactification, you have a lower limit on R beyond which the theory becomes unstable. So you cannot separate the mass of bosons and fermion at delta M more than something which has to do with essentially 1 over square root of alpha prime. If you try to separate them more, then you get tachyonic modes. So that's the basic lesson. This is the Scherk-Schwarz mechanism. The second lesson of the Scherk-Schwarz mechanism, you see it already from this partition function, that the partition function, you have introduced some terms that don't vanish if you impose V8 equal S8 equals C8. So in other words, you back react on the vacuum. And if you want, you get an effective potential that depends on the radius of the dimension that you compactify. And the potential is typically power, so it's a runaway potential, as they call it, potential without a critical point. So as soon as you break supersymmetry, R is not anymore a modulus like before. Before, if I changed R, there was no effect on the vacuum energy. It was a free parameter. Now it costs because you get an effective an effect at the one loop level, because this is this partition function come effective from the one loop. So R is not a modulus anymore, which is good for physics because it means that this undetermined parameter would be fixed. But you get instabilities if you try to separate bosons and fermions too much, more than that typical limit. And then with R, you will get a power-like contribution. In other words, you get a runaway potential. This pattern, although I explained to you in a very simple context, is sort of recurrent. So the Scherk-Schwarz mechanism gives you the possibility of separating bosons and fermions, even considering lattice more complicated than this. You cannot separate them too much, more than if you want what is dictated by the string scale. Otherwise, you you lose control of the theory because you get instabilities. And then, as usual, when you break supersymmetry, you get a back action on the vacuum, and this manifests itself in the fact that the contribution to the vacuum energy is a function of R, and you will see that it has a behavior on R which is runaway. I mean, of course, I'm not proving it 100%, but I gave you the basic ingredients. So this is a general pattern. You break supersymmetry, you have the advantage that some undetermined parameters are not undetermined anymore, determine some sort of potential, but the potential is typically doesn't have critical points, and moreover, there is an upper limit, sorry, to the mass separation between bosons and fermions, beyond which you lose control of the theory. So in the last lecture, now I'll stop. In the last lecture, I will give you some hints that this gloomy type of situation, in a situation in which, gloomy in the sense that everything becomes much more difficult to control. So in some sense, we should raise our hands and say that there are some cases in which we have to deal with this stuff a priori, it's inevitable, which will be those non-supersymmetric theories in 10 dimensions. I'll show you that nonetheless, there are surprising hints by describing to you some attempts that have been taken over, made over the years to try to go beyond supersymmetry in a case where it's inevitable to do that. So I told you that there are three non-tachyonic 10-dimensional theories which have either nonlinear regularized supersymmetry or no supersymmetry at all. And the portion of the effective action of interest for the backgrounds for two of them, so for the UOSP 32 and for the U32, the effective action and I will write them in the Einstein frame, okay? Effective actions for these theories contain these terms plus some form terms, form plus gauge fields if you want. And then there is the tactile potential. For these two theories, in the Einstein frame, the tactile potential is this one. For the SO16, cross SO16 theory, the gauge field and tensor terms, as we saw, are different. And also the tactile potential is different. The reason is that this tactile potential comes from the projective disk or the disk. So in the string frame, this would be e to the minus phi. And this one in the string frame would be integral, would be really a cosmological term if you want, in the string frame, because this exponent reflects the order perturbation theory that it comes from the Polyakov expansion, or the Euler character, if you want, of the surfaces. And so the issue is what you do with a theory like this. And clearly you cannot work at the whole sheet level because the spectrum is not reliable because the background has been modified. For instance, since you have a potential like this, the equations that you will get, gravity will involve this as an energy momentum tensor, and the scalar equation, which is easier to see from here, is somehow box of phi, covariant box of phi equal the derivative of the potential. So if you have an equation for the scalar, which is box of phi equal the derivative of a potential, if the potential has a critical point, then you have a solution in which the the scalar is the critical value and is constant in space. So if the potential is a critical point, you can put the scalar at the critical point, V prime is 0 there, and then the solution phi equal constant to that value in space solve the scalar equation. If the potential is run away, like in this case, there's no critical point, so the scalar must have a non-trivial profile. This is what happens, right? And so there was a very important step forward made by Dudas and Murad in 2000, who found a solution for this system, for both of them if you want, that if you want is the counterpart of circle compactification for this system with the Dilaton tadpole. But the differences are striking, and let me show you what happens. So I'll give you let's discuss this case. The other one is similar but more complicated. It's not worth getting into details. I mean, you find it in the literature. So in this case, the metric has this form in a certain coordinate system, which you can I will write it in the simplest possible way. So there is a variable that characterizes the solution, and the internal space, differently from what happens in circle compactification, is an interval. Let's see what the length of the interval is. Well, we have to integrate the square root of this stuff. So square root over 2 over 3t integral e to the minus 3/4 u du over u to the 3/4. That's the length of the interval, right? Because the fact that u goes from 0 to infinity doesn't tell you the length is infinite. You have to use the metric to see what's happening. And now you find two interesting facts. First, that this thing is finite. And second, that it's proportional to 1 over square root of t. So very differently from what happens in toroidal compactification, now the tadpole potential determines the size of the internal space. It's not a modulus anymore. It's fixed. So the pattern continues, not that like we sort of foresaw in the other case. Now, but there is a big novelty, no? Because if you have an internal space which is a circle, then there's no special point. Here, on the other hand, we have something with two special points at the ends. And what happens to the dilaton, which is the string coupling? Well, when u goes to 0, e to the phi goes to 0, so at this point you have weak coupling, I mean zero coupling really. At this point you have strong coupling. And the dilaton is forced to run because the running of the dilaton essentially is forced by the fact that you have no critical point in the potential, and the back reaction on this on the metric determines the internal space. So you have these key differences. Now, there are other solutions that you can find. Some of them resemble the ADS cross S solution that is so cherished in the supersymmetric context. But what happens is that typically there are instabilities in these backgrounds. For instance, the ADS cross S solution has instabilities due, if you want, to the mixing between Kaluza-Klein excitations with the ones that are present also for internal quantum number 0. So there are mixing that produce negative mass squared, or better, in the ADS cross S solutions, violations of the Bredt-Lone-Friedman bound. because you may know that in flat space, what is problematic is a tachyon. In ADS space, you have a range of tachyonic masses which are still allowed. Now, when you go and study this solution, on the other hand, you find something very surprising. The surprising story is the following. You want to study perturbations of the metric and the scalar field, no? And then there is an issue of gauge that cosmologists know very well, no? That you have to make a choice of gauge which corresponds, if you want, to distributing the actual perturbations between gravity and the scalar field. Somehow they're mixed, no? And there are perturbations of different type. There are perturbations of gravitational type. The discussion parallels a little bit what people do in cosmology. In that case, you have gravitational perturbations, you have scalar perturbations, which arise precisely because of the presence of the scalar field. Now, the equation for the scalar perturbation is apparently shockingly complicated. So let me tell you, you do the following thing for the metric. First of all, you write the metric in what is called the conformal gauge or conformal coordinates. And the scalar perturbation is this deformation of the metric. The compactification goes from 10 to 9 dimensions. I didn't stress it, but it's manifest here. The 9 dimensions, this is the length element in 9 dimensions. So there is a warping due to the behavior of the internal space, but you end up in 9-dimensional flat space. Okay, so it's a compactification to 9-dimensional flat space. Not on a, that's why I said it's a generalization of the circle compactification. Because like in that case, you end up in flat space with differences like this. So this is the metric. Then you can express the perturbation of the scalar. Phi prime is the derivative with respect to the internal coordinate, but now the coordinate system is slightly different, so never mind the absolute detail. Now, the important thing is you get an equation for A is the scalar perturbation, which looks like this. So it's rather unfriendly. Huh? And so A is the perturbation, the rest is the background. But you see, it's an ordinary differential equation, of course. And the issue is the eigenvalue spectrum of this equation. It's essentially a Schrödinger problem. So you want to find what values of m squared are allowed. Looks pretty complicated, right? I mean, because this omega depends on it is essentially the solution. The phi is the derivative of potential with respect to phi, so it's proportional to v, but it's an exponential of phi. Very complicated. However, what happens is that by change of variable, you can recast your problem. The trick is a standard trick in the theory of differential equations. You can eliminate this term by an exponential redefinition of A. But what is interesting is not this, which is a standard fact, but is that this H has a form which is very suggestive. Let me use a different symbol. Script A. Where, in fact, So if I define A of Z to be this quantity, the differential equation is of that form. You see why it's interesting, this type of form? Can you see it? What does a form like that remind you of? Exactly. So the only thing is that it's not a conventional harmonic oscillator because you have these operators which are more complicated. Nonetheless, there is a positivity issue for this stuff. Provided you choose proper self-adjoint boundary conditions. And they have to be self-adjoint boundary conditions because when you study perturbations, you want to study solutions with a complete set. No? Why do you want a complete set? Because you want to describe an arbitrary perturbation. So you must select the boundary conditions at the end of the interval that grant you a complete set of modes. And then within that complete set of modes, see whether m squared is positive. To go really into detail, if you are experts of this stuff, this form doesn't quite grant positivity. Generically it does, but there are, if you want, sick boundary conditions where this thing cannot be positive. Generically it's positive, and what is interesting is that you can also prove that this quantity is positive. So this means that with generic boundary conditions, the system is stable. It was absolutely not obvious. I mean, somehow this compactification, no matter its complication, no matter the fact that the dilaton goes at strong coupling at one end, but as soon as you move away a little bit from that end, the coupling becomes moderate, it's stable. This was a big surprise. It was not you. But to my taste, the biggest surprise comes when you look at cosmological solutions. Because you can look at cosmological solutions for this system. If you want, to some extent, they are similar to this. The standard case for the orientifold can be obtained continuing analytically this solution. But if you look at it from a different vantage point, then it becomes very, very surprising and interesting. Let me try to give you a sketch of this so that I leave you with a feeling of what in principle can be done. Now, this is not a final story, so you should take it with a little bit more critical standing with respect to the standard, the well-established old stuff that I told you, because this concerns recent and or ongoing research. So there could be some subtlety behind the corner, but the result is quite interesting. Instead of considering that theory, let me make the following generalization. So let me consider the theory with variable with a certain range of gamma. Gamma equal 1 corresponds to the orientifolds. Gamma equal 5/3 corresponds to the SO16 cross SO16. Okay? Now I'm not looking at perturbations anymore. I want to look at the equations of the background themselves. So I want to look at the cosmological evolution which is driven by an exponential potential of this type. So let me write down the equations for that system. So you write down the equations of motion for arbitrary value of gamma in that range. And then the equation, first of all, if you try to study this system in cosmic time, it's not solvable. So these quantities are functional this time. Let me call this guy tau, not t. Because clearly you see it's not cosmic time. Cosmic time would be defined by dt equal e to the b. But if I work in cosmic tau, the equations are unsolvable. If I work with this parametric time, the equation take a very suggestive form. Where A is this quantity. And then you had the equation of motion for the scalar. So things combine so that once you solve the second order equation for phi, then you determine A dot for an expanding universe, because this thing tells you that A dot is 1 over square root of d minus 2 d minus 1 times the square root of t plus 1/2 phi dot squared. So the issue is to solve that equation and see how it behaves as a function of gamma, because we are exploring the behavior of the solutions as a function of gamma. Let me do some redefinitions that simplify these equations without doing them explicitly. But you realize that essentially rescaling what I mean by A, phi, and this parametric time, I could write them in this form. The reason why I do that, because it's simpler to follow the argument. But you can work similar in the other form. My question is, did you ever see in classical mechanics an equation that resembles a little bit this one? Did you ever stumble upon something like that? Resemble, I didn't say identical. Huh? Let me try to simplify it a little bit and see if it becomes more familiar. Sorry? No, damped but not harmonic oscillator. How about that? If you put phi dot equal V, this is V dot plus V plus gamma equals 0. Now, gamma is usually put in front there, but as a damping factor. But this is the equation of the motion in a viscous fluid, if you want. So what characteristic does, or if you want, let me write it differently in a more convenient, more standard notation. mv dot plus bv equal f. What characteristics does this motion have? Well, if b is different from 0, there is a limiting speed, which has f over v. And if b equals 0, it's an uniformly accelerated motion. So when b goes from 0 to non-zero, the type of motion changes drastically. Let's see what happens with this solution here. I work on it with this simplified form. It's essentially a redefinition of that, but you can translate it direct, just to not to bring along coefficients and complicate matters. So what we are interested in is the type of behavior that is implied by this equation here. And but the universe starts from the initial singularity, no? So let's go close to the initial singularity where phi dot is very fast. No? Everything moves very fast at the beginning. Okay. So this equation here becomes approximately phi double dot plus phi dot absolute value of phi dot plus gamma phi dot squared approximately 0. Okay. Now clearly this equation admits power-like solutions. Admits a solution phi dot equals C over tau. Tau is a redefinition of that tau, but never mind, I mean, because I wanted to have simple coefficients so that you see what's going on. Or if you want, we could also do things in a different way. And imagine that we do this limiting speed story, no? Kill this guy. You kill this guy and you get that phi dot approaches gamma divided by square root of 1 plus phi dot squared. No? So it seems as though you get this limiting speed. You know? And sorry, no, I made a mistake. It's not the best way to solve it. I apologize. And so if you want to study this system and go to this limit, you can solve for phi dot. And I tell you that phi dot, the limiting speed, only exists if gamma is less than 1. You can substitute because if this is phi dot, 1 plus phi dot squared is 1 over this thing over 1 minus gamma squared, so without square root. But you see that that solution, I mean, this thing solves the equation, but it only exists when gamma is smaller than 1. So you already start to see that this equation has a completely different behavior for gamma less than 1 and gamma larger than 1. I remind you that up to the redefinition that I didn't carry through in detail, gamma equal 1 separates the 10-dimensional non-supersymmetric strings from other models which have nothing to do with string theory. In particular, gamma equal 1 is the orientable value. So let's go close to the original singularity. Let's see what happens. So we saw that gamma should be smaller than 1 to get the limiting speed. The limiting speed is the translation in this language of an old result in cosmology that people knew for a long time, because for phenomenological reason, people always studied this solution for very small gamma. And the limiting speed describes what is called the Lukin-Matarese attractor. But in string theory, we're not interested in small values of gamma. So let's see what happens if we take this thing. So substitute, and here you get minus c over t squared. And here you get c absolute value of t over t squared. And then you get plus c squared over t squared. So you get an equation for c, right? So let me write c equal absolute value of c times epsilon, where epsilon equal plus or minus 1 is the sign. The t squared cancels, so this guy becomes minus absolute value c times epsilon. The other guy becomes epsilon absolute value c squared. And the last guy is tantamount to absolute value c squared. And here there is a crucial gamma that I had forgotten to write, and here also. So if I want non-trivial solutions of this type, I must have absolute value of c different from 0. And let's try to solve this equation here. First of all, I divide by absolute value of c, so you get, and I multiply by epsilon, so that epsilon is only in one place. So what do you get? Minus 1 plus absolute value of c from here, plus absolute value of c times gamma times epsilon equals 0. And so the solution is c equal 1 divided by 1 plus gamma epsilon. Do you see a problem with this solution? Do you see an interesting feature of this solution? What happens? In principle, you have two values of epsilon. But is, huh? Gamma equals 1, epsilon equals -1. That's a pole, but in any case, even gamma larger than 1 equal epsilon equal -1. Because on the left-hand side, you have something positive. It's an absolute value. So it means that the solution of this equation changed dramatically at gamma equal 1. At gamma equal 1, the dynamics changes completely. Now let's look at it intuitively. Suppose that gamma is very small, okay? Gamma is giving you an exponential potential. So if gamma is very small, the potential eventually becomes 0 everywhere, no? Actually 1, not 0. I drew it well, I didn't say it correctly. Now it becomes a constant. So if the potential is a constant, there is nothing wrong if the scalar emerges from the initial singularity from the left or from the right. So you have two independent solutions. Then you increase gamma, and at some point, when gamma becomes 1, one of the solutions disappears. And what is the solution that is left? You see it from here, because since epsilon on 1 is the only possibility, it means that phi dot is positive initially, which means that the solution is something that climbs up and then descends. That's why it's what's called the climbing scalar. And now you say, who cares? Okay, it doesn't descend. But remember that e to the phi, up to all this redefinition, is the coupling constant in string theory. So it means that the 10-dimensional non-supersymmetric strings in a cosmological setup, which is not so exotic, because these cosmologies are typically related to the early inflationary phase, with an important proviso. What I've told you is not enough. It can be completed into an inflationary scenario. Tell you that the coupling constant can always be weak throughout the cosmological evolution. Not only can always be weak, but in some sense, when the scalar is forced to climb up in the early universe, it accumulates some energy that can be released to start inflation on the way back. Of course, the top-down arguments from string theory are not enough to do that. You have to take your potential, which is t e to the, say, 3/2 phi, and add to this potential a certain term with an exponent, say lambda phi, where lambda is less than 3/2. In fact, it should be less than a value below this in order to allow an accelerated expansion. Then you can have a nice picture, because first of all, you can prove that the climbing or not climbing story is always related to the fastest exponential, as it's also intuitively clear, because this term here dominates for phi negative, and this term here dominates for phi positive. So you have, so to speak, a situation like this. Sorry, this is essentially the result. But the scalar emerges like this because it cannot do anything else because of the exponential barrier. Goes on, climbs, bounces back if you want, and then inflation can start. In particular, if the lower potential, the second guy, you can put anything you want there, is the Starobinsky potential, then you can have a situation like this. So this is the hard potential due to string theory. And the scalar cannot emerge from here because it's forbidden by this climbing story, what I showed you, because here this guy dominates, so the argument holds. The scalar can only come from here, go up to here, bounce, and then, so you can have an inflationary phase following a faster phase at the beginning, which ends up in reheating, as is usually the case. Why is this type of scenario potentially interesting? Because I always found it a bit unnatural that in the early universe, you have everything going very fast, and then you have this scalar that is rolling slowly, 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 slowly. You can ask, how could it get to roll so slowly? Well, in this case, it cannot do anything else if you want. Of course, there are some parameters. Don't take the words as a verbum, because you have to arrange, for instance, this region to be large enough in order that you have enough e-folds. But nonetheless, you can have a scenario in which the scalar starts fast, as it should, then it loses energy, and then it starts an inflationary phase. From the point of view of physics, what does this tell you? Well, you know that there is this famous plot of the spectrum of the CMB, no? And the famous plot of the spectrum of the CMB goes more or less like this. You know, there is this famous peak, then there are other peaks here, and there is this region, but if you magnify this region, what you would predict is like this, and then it really actually goes down a little bit. Now, of course, if you're careful, there are error bars, and there are even conceptual error bars in that region, for a reason that those of you who have played a bit with cosmology know very well, which is called cosmic variance. Essentially, we take pictures of the sky from the Earth, and when we look at high multiples, we are looking at smaller regions, and so we can do the statistics on more smaller portions of the sky, and the more we have them, the less fluctuations we have. But when we go down here to the first few multiples up to 10, where the thing starts to deviate, you can say, okay, it could be a fluctuations, but the quadrupole is really very low. And now what happens if you have an inflaton that goes fast, as dictated by a situation like this and then decreases? What happens is that the Chebyshev-Mukhanov spectrum, which also reflects itself in the distribution of galaxies, at some point it gets to deviate. So this is the spectrum, and then this is what you get typically. Well, not like this, it goes to zero like this. So in other words, there is a characteristic scale at which the spectrum starts to deviate from the power-like spectrum of Chebyshev and Mukhanov. And if this were a correct statement, the same situation would be reflected in the distribution of galaxies. So the first idea is to look at the CMB and to do it together with people that have more experience on the subject. And what happens is very interesting, that you can parameterize this deviation due to the fast to slow rolling doing something similar to going from a massless to a massive propagator. And then you can look at the sky and try to see whether comparing with the CMB, you can get a non-trivial detection of delta. If you get a non-trivial detection of delta, you can have an evidence that something of this sort is happening. Not exactly this type of phenomenon, but this type of phenomenon has two other, this is, if you want, is a post-diction if you get it, because you know that the spectrum goes down. And you can just detect at what scale delta this occurs. So you compare with the CMB, and then you have this famous picture of the sky where everything is filled by dots. But this picture is for the public, it's not for the experts. And the reason is that the horizontal part of that is the galactic plane. So the galactic plane is polluted by many sources of light. And so the cosmologists look a little bit away from the galactic plane and try to simulate the region in between. So strictly speaking, you shouldn't believe this picture as such, but you should believe a picture with, where of course there are opposite needs. On the one hand, one wants to reduce this region left out as much as possible to look at the whole sky. On the other hand, the clean region is outside. So one can do a comparison with different masked regions. This region inside is called the masked region. So you can mask like this. So what happens, to make the story short, is that with a reasonable masking, when you go away from the galactic plane a bit, delta is detected at 3 sigma. Fine, this is interesting. What is delta? Of the order of the cosmic horizon. Fine, so it's not a number which makes no sense. The question is, do you have anything else to add to this picture? In fact, there is one thing that one can add to this picture. That at the scale delta, where the spectrum drops, the tensor to scalar ratio grows by about 1 order of magnitude. This is true in all these models of this climbing story. Of course, we haven't seen the tensor perturbations, so it could disappear altogether, this story. But in principle, it could even help us to detect tensor perturbations if this drop in the power spectrum is attributable to the fact that the inflaton is not slow rolling all the way. Another possible source of information has to do with the non-Gaussianities, and there are reasons to believe that in the same region non-Gaussianities should also increase. So this only to give you an idea that in an apparently ill-defined system, very complicated, that you cannot study for string theory with string theory all the way, but you have to do it approximately with effective field theory, something absolutely magic is happening. Precisely at the value that string theory predicts, the behavior of these solutions changes completely. And there is even another interesting story that I have just time to mention in words, namely that you can also study perturbations of these solutions. Now the issue is not how perturbations evolve in time. No? And now what happens is that if you study the perturbations of these solutions in a way similar to what I was doing before, but it's not an issue of mass or square mass. It's an issue of seeing whether perturbations decay during the cosmological revolution or not. You find that perturbations, tensor perturbations this time, typically decay, but the very, very large scale tensor perturbations have a logarithmic instability. So if you take it at face value, it means that isotropy has an instability. But you remember that the big puzzle is that we start from 10 dimensions, and who tells us that we should go to 4? There's no reason. If supersymmetry is left around, everything is completely inert, and going to 4 is a choice. It may be, this thing may be telling us that once you take into account the breaking of supersymmetry, then you may have ended up in a 4 dimension, a global instability. Doesn't tell you why you ended up here, but tells you that the global instability. So this is what I wanted to tell you. I think that we can stop.